Hi, in this video, we're going to take a look at graphical representations of composition data. Okay, so remember that composition data is data where we have non-negative values, preferably positive. So we can have zero, we prefer not to. And on every single observation, all of the data fields add up to a constant value. Typically, we'll go with that constant value being 1 for like each each field is measurement is the proportion, the fraction of that amount, or we could have the constant sum of 100 if we wanted percentages, or we could do 1,000,000 for like parts per million, something like that. So composition data is all over the place. It's very useful. Imagine that I'm doing soil samples. I come up, I scoop some soil, and I want to know the composition of the data. Well, sometimes when I scoop the soil, I get a lot. Sometimes I get a little. Different people, collecting the data, they get tired. Things change over time. And so we're not so interested in the exact amount of each thing that was in the sample. We're actually more interested in proportionate to the rest of the sample, how much was in there. And so composition data is, where we get into this. Now, something that is very important to remember that in composition data, if I only have 2 fields involved in an observation, then I will have perfect negative correlation. Why? Because as one goes up, the other goes down. Across the board, when I have more than 2 multiple fields involved, when one goes up, somewhere something else has to come down. So in composition data, the analysis is not as straightforward as with regular old data because we have that relative aspect going on. And so we're going to pull in some tools to help get us into it. All right, so for graphical representation, like every data science project is going to require us to understand our data, and more than likely we're going to have multivariate information going on that we want to know how is my data in a multivariate aspect related to each other for each data field. All right, so now if I go through and I do univariate analysis, all right, that's going to be very helpful for me to understand one field at a time, but that's not going to tell me anything about multiple, relationships. Univariate is always where we want to start because I want to understand the simplest stuff first and then baby step into more complicated situations. So I'll always do like my histograms, my dot plots, box plots on my univariate data first. Then we can get into individual bivariate data visualizations. Now, here I'm going 2 variables at a time. All right, well, if I've got a lot of variables involved in my project, 2 at a time can take a while to get through. All right, so that's not really so great, but it's a tool. But still, when I'm looking at 2 at a time, I can't consider the whole situation. And so what we want to do, we want to get into some tools that give us a more comprehensive view. Now, as we go through, in real life, we want to do univariate, 1 variable at a time, and then I get into the more complicated plots. So when I'm looking at 2 variables at a time, I'll want to be able to look at multiple at the same time. That way I get one shot real quickly. Now, something that's really, really cool and really neat about composition data is that we have something called a ternary plot. All right, so in a ternary plot, I take 3-dimensional data and I get to represent it on a 2-dimensional plane. So I can completely represent my data off of a 2-dimensional shape, an equilateral triangle, without having to do any weird geometry or projections or anything like that. There's no data lost. Like if I do higher dimensional data in regular situations, if I do principal component analysis, the principal component plots, I have a compression of the projection. Here, the ternary plot, when I have a composition of 3, I have no information loss. Really exciting, really neat. Now, we'll take it even a step further in this video. In fact, if I have a 4 data field composition, there are 4 variables in my composition, With 4, I can represent my data in 3 dimensions. So I can do a 3-dimension plot and understand what's going on. All right, so here, let's go ahead and talk about the different types of plots that we can use. So I can go one by or pair by pair and look at regular old scatter plots to understand my data. And there's other visualizations we can do, but that doesn't really get us past, it doesn't get us to where we really want to be on this. And we'll talk about the ternary plots and the 3-dimension version, and then we'll talk about parallel plots. We're going to use the Win-Darling dataset from the GM Geostats package. We're going to restrict our focus to just a few data fields. And here I'm setting it up so that I have my residuals as a data field. All right, so what we're doing here is there's 3 fields that we're interested in. And then we're going to say all other aspects. So these are from soil samples. There are 3 things that we're interested in, primarily for the project. And we're going to say all other items in the soil is in the residual. And so here I'm setting up so that I have that residual of everything else category. And that's what I have in composition residual. Now I'm doing this a little bit different than the textbook. I like to explicitly name everything. And notice that my names are very long when I type out my code. All right, so let's do a ternary plot on this. So I've got several of them going on. All right, so let's go ahead and let's focus on iron, silicone, and aluminum in the data sets. And I'm going to disregard everything else. So when I do this, I need to be mindful that in my composition, I'm not counting for everything. I'm only counting for these 3. And let's go ahead and do a ternary plot. And I'm going to use ggplots approach to this. And so this is in ggtern, which is in, let's see, I have to, yeah, ggtern is in the ggtern package. It's got its namesake going on. And now I can plot it. All right, so what's going on in this plot, in this equilateral triangle? This is a 3-dimensional plot on a 2-dimensional surface, and there's no information lost. Why is that? Well, this is geometrically possible because if I know silicone, I know aluminum, I know everything adds up to 1, I know iron automatically if I know the first 2. So by knowing 2 out of the 3, I know the third one, makes it mathematically possible to have a 2-dimensional representation of 3-dimensional data with no information loss. Okay, so this corner here is saying that we have 100% in aluminum and 0, in silicone and iron. This is 100% silicone, 0 for aluminum and iron. This is 100% iron, and 0 for aluminum, 0 for silicone. All right, so now this point in the middle is 1/3, 1/3, 1/3. All right, and I manually put in these dots to make the referencing easier. So here, this is we have a situation where all of them are equal amounts. The closer a point is to here, the more even the sample is of the 3. And dots that are close to this corner have proportionately more iron than the other 2. If it's closer to here, it has more aluminum. If it's closer to here, it has more silicone. All right, so now what is going on here? Iron is 0, and we see a gradient of silicone. So here we have 100% aluminum, 100% silicone, and as we go along the edge, we're decreasing the amount of aluminum, increasing the amount of silicone. Here we have 0 aluminum along the edge. As I go from right to left, we're decreasing the amount of silicone, increasing the amount of iron. Here we have 0 silicone. And as I move along this edge, we're decreasing the amount of iron, increasing the amount of aluminum. And these red dots here are the 50-50 marks. So this point here is we've got 50-50 for aluminum and iron, 50-50 for silicone and iron, 50-50 for silicone and aluminum. And we can see that we have proportionately more iron in most of our data points than the other ones. We also see, here we have more silicone than aluminum or iron, and so we get an idea of what's going on. Like these ones are on on the edge or close to the edge have very little aluminum. Now, something else I've also done is you'll notice I have transparent data points. These transparent data points, you see that when they go on top of each other, it gets darker. So we have some points over here overlapping. And so I can see visually where I have more data appearing. Now, the author gives us a way of plotting also. And we see the same representation, but it's not as fleshed out. Same thing, we reach the same conclusions, but we get a little bit more precise representation here. Now we can also do a four-dimensional tetrahedron plot, and it's a three-dimensional thing. And what will happen if you run this in RStudio, it'll pop up in your system, on your computer, and you can rotate the tetrahedron around to be able to see the 4 points. And here we're able to represent residuals also. And so we can get a more complete representation. Now, three-dimensional plots, they're really sexy, they're really exciting, but my experience, my opinion, is that they feel more informative than they really are. I don't put a whole lot of stock in storing them because you have to rotate and figure out what's going on. It's not consistent. It's very attractive when you're learning data science. So you start trying three-dimensional plots to get more information in. My advice is actually don't really worry about it too much. But if I had a four-dimensional composition data, I absolutely would do this to get a better idea of what's going on, and then use the ternary plots to get a more complete picture going. All right, so now let's talk about parallel coordinate plots. Okay, so what I'm going to do is I'm going to create a grid of plots, and I'm going to use a consistent row axis and column axis with other aspects of the grid. So what's going to end up happening is on the first, let's say the top row, every single vertical axis is going to have the same variable and the same scale. On the second row, every single plot is going to have the same vertical axis variable on the same scale. And so each row, as I go down, will have a different horizontal or a different vertical variable, and we'll have the same scale across. Now, I'll have also columns in my grid. In a particular column, every single plot that I have in the grid will have the same horizontal axis variable on the same scale. And so this enables me to look at things individually. So, so the axes of the variables are parallel and share the same scaling when I look across a row or up and down on a column. So this enables us to track individual aspects of our data set. Specifically, we can track individual observations through when I figure out like, oh, hey, what's going on with this? I see its vertical axis, I can move across. Oh, what's going on with this point? I see its horizontal position, I'll move up and down in the column. All right, so parallel plotting is the default behavior of pairs, and the ggpairs package, sorry, ggally packages ggpairs function. Some parallel coordinate plots use the same or different axis scales. It is possible to change the scaling on individual plots. That's more of a faucet plot. That's really easy to produce in R. But generally speaking, we use the same scale consistently. And the reason for that is that it makes it easier to compare, to understand the multidimensional aspect, but also it sets it up so that in my limited plot space on the screen, using the same axes scales every single time, I can actually take up less space of that real estate for the visualization. And also when we do this, we make sure that we have the same like transformation magnitudes on across the entire column or across the entire row. So let's go ahead and do this. So first and foremost, I'm going to use ggally, ggpairs function, and do some more basic plots to show you examples. And so first and foremost, I'm just going to give you the correlation between different variables to make this easier to interpret. So along here, every single vertical axis is for iron, Every vertical axis is silicone, every vertical axis is aluminum, every vertical axis is for residuals. This column, every horizontal is for iron, every horizontal is for silicone, every horizontal is for aluminum, and every horizontal is for the residuals. And so off the diagonals, you can see what the correlations are because I chose to put correlations above the diagonal and below the diagonal. I control what you see above and below the diagonal with this function. And what GG pairs does is it goes ahead and it puts in a distribution here. And you can see that we saw a lot of like heavy iron samples when we looked at the ternary plot. We can see that here very clearly, where that we have the distribution more to the right. Along the diagonal, we see the distribution of the variable that's in the row and in the column. And you'll notice that I have very consistently negative correlations going in there. We would expect to see this. All right, so now I'm going to put on a scatter plot with a linear model onto there. Also, something that I like to do is I like to color my points. And here what I'm doing is I'm coloring by the amount of residual. So the residual for my analysis in this particular situation is going to be my baseline level. So one thing I like to do when I do my plots, I like to color the points by an important variable. Like if I have a target variable in supervised learning, I'll put that in. And so here I set it up so that approximately 1/3 of the data points are red, approximately 1/3 are green, and approximately 1/3 are blue. Now they're being red is for let's see, let's look at the residuals. All right, so red is for the smaller residuals, blue is for the greatest residuals, and we can see that we've got a good amount of clumping overlapping. And so 1/3 of our data, the red is pretty well spread out, while the green is about 1/3 of our data, the blue is about 1/3 of our data. And we can kind of get a feel for a linear model. All right, so like here, I can see what to me looks like a linear trend, but these points here pull the linear model away from the visual trend. Something that's interesting to know if I wanted to start doing linear regression. And we can start seeing that we have points down here going on. We see this like horn shape, which is common in composition data, by the way. But here this is adhering pretty well to the line. Here we definitely have some deviation. Now we can also do a lowest curve, so this is a more flexible curve than a straight line. And so when I see it's pretty straight, that's an indication that we're capturing everything that's relevant with a straight line. And so like here, I would definitely prefer a straight line if I was to do modeling on these pairs. But we can see that there's some curvature here and there. Now, when I see like crazy bends, that's usually an indication of small data, and that typically happens far to the left, far to the right. That's a part of it. And something that's important to notice is like severe deviations from points that we definitely have going on. And we can also use a contour plot here at its density to do this, to get an idea of the distribution of our dots. Now, remember all that over plotting that was happening with the blue and the green? Here we can see that, practically speaking, when I look at the raw data, the points are just stacked on top of each other. They're really, really tight. The vast majority of my data is just in one single spot on this scale. And so this is making it tougher to understand what's happening. And so I'm going to want to try something else. So I'm going to go ahead and I'm going to try centered log ratio transform data. And I'm going to go through and do these here. So I looked at the raw data. I go, you know what? The raw data is not the way to go. It's too clumped up. Let's go ahead and try a transformation. From the previous videos, we know that centered log ratio transform data has a lot of nice theoretical properties. So let's do that one. And so I'm going to do the transformation. So here I'm transforming centered log ratio transform. And now I'm going to take the correlation. All right, so here we're seeing, these values have shifted. But if I remember correctly, the ones that are positive are still positive, the ones that are negative are still negative. And now I see more of a spread out of my data, which will usually be easier to work with. Now let's just do the straight points by themselves. So remember, blue is 1/3, green is 1/3, red is 1/3 of my data, and and the color is being determined by the residual value because the residual is my reference level. All right, and so we can see that we've got more spread on the residual here in the red, and then after that blue and then green, we have some clumping going on, which we see right here in the density plot. And so pretty solid line, and things are looking less horn-shaped. And so this is making me feel better about my situation with my data, that I'll be able to analyze this better. Now we can go ahead and use smooth LM to put in a linear regression model. And across the board, overall, I feel better about these linear relationships. Not perfect fit, but that's okay. I mean, the data is what the data is. We can also do a lowest curve instead. And so, we can see that we've got some curvature going on in the lowest curve. If I see, severe curvature, I would not consider a linear model. Here, this is deviating pretty hard. So like these points here, I would be interested in studying more. So we can see these are the very low iron values. Now, when I've got overplotting, like my dots are stacked on top of each other, so I can't see them, that can make it indistinguishable. And what can happen is I have a bunch of dots on top of each other, a few that aren't, and these guys look like really heavy outliers, and they can screw up the interpretation. And so what I want to do is I want to set it up so that if I have this overplotting problem, I want to do something about it. I want to address it. I want the best visualization that gives me the correct conclusions on what's going on. And so ways that we can do this is that we can jitter the points by randomly adding or subtracting to the coordinates, like usually like a uniform normal, or maybe a random uniform, perturbation onto it. This works best when I have small data sets with overlapping points. We can also vary the point diameters by the number of points that are sharing the coordinates. This works best when we have discrete values. We can also make the points transparent. This is my personal preference with the alpha parameter in ggplot. And so here, overlapping regions, overlapping dots are going to appear darker, so I can visually interpret what the density looks like. And then we can also use bivariate kernel density estimation. The author of the textbook created a really good, really astounding tool for this exact use. And I'm going to get excited for it. It's colorful. It'll be good when we get to it. All right, so now here what I've done is I've taken each point and I've rounded them in a manner so that points that are approximately the same have the same coordinates, and then I counted the number of times that they appear at a location. And so then we have bigger squares or bigger rectangles to indicate where we have larger frequency. Here, I don't like the plot for this particular data set. I played with the rounding to try and get something better. I've used this in the past professionally of increasing the diameter to show more frequency, less frequency, and very successfully. But on this particular data set, I don't like the results. This works best if you have very distinct, discrete values. We can also do a density plot. Now here we get a better view of what's going on. Things look more elliptical in my densities, which might, if it's more elliptical, that's very much a better situation instead of having everything just crammed on top of each other. All right, now let's look at how the packages and base R handle this. So if I just do regular old pairs, I get a scatter plot. I get scatter plots, just like we saw before, but I don't have the colors going on. This is a little bit more blunt. You'll notice that by default, R uses open circles to help address the overplotting aspect. We can also do a pairwise plot of the bivariate distances using a heat map. So if it's a hot in the heat map, we have more points there. And so I really, really like this plot. I think that this is an excellent plot. This shows the value, this shows the information I'm going for when I'm doing this. Now, when I look at the interpretation of this, remember that if I conclude that I have normally distributed pairs, so bivariate normal, that doesn't mean I have multivariate normal across the board. Well, multivariate normal for all four of these in a four-dimensional normal distribution is a very, very, very high bar to have to achieve. And so even if I conclude that I have bivariate normal on every single pair, that doesn't mean I conclude correctly that I have multivariate normal. In real life, we usually just go with the pairwise plots. It's good enough. Now, on this next one, what we're going to do, we're going to consider the reference level for when we do a histogram. So what we're going to do, we're going to do a kernel density estimate and a histogram for each pairwise log ratio using the row variable as the numerator and the column variable as the denominator. All right, so the column is our reference level, and then our row is the value that we're actually looking at. And so here we can go through and just see the differences throughout and get an idea of this pairwise aspect. I've used this concept, a similar concept at work, where we take the target variable and then we group them by the target variable average values, just like we have the bars here, and perform analysis that way. So this is similar to some plots I've done at work. All right, so now let's talk about the pairwise plot of normal quantiles. All right, so what we're going to do is I'm going to do a normal QQ plot, just like an introductory statistics, but we're going to do things a little bit different. Above the diagonal, we're going to do the pairwise differences. Below the diagonal, we're going to do pairwise sums. Okay, so when I look at an individual plot, it has a row variable and a column variable. Above the diagonal, I'm going to take the difference of those two. Below the diagonal, I'm going to take the sum, the addition of those two. And so I'm going to use this to get an idea about what's going on with the distribution. Remember that joint normality of the data implies normality in all marginal distributions, although the reciprocal is not true. Now, when we look at the normal QQ plots, the middle dot, if the middle dots deviate from the line, so like the middle third or so, that means severely not normal. When the data is continuous, unimodal data, and it's reasonably well-behaved population, we can use the normal plots to better understand the data and understand the distribution. And here are the rules for what's going on. If I see that above the line on the left, above the line on the right, it's a skew right distribution. And for example, gamma. All right, and if I see on the left, above the line on the left, below the line on the right, that means we have light tails, for example, uniform distribution. If we see below the line on the left, above the line on the right, then we conclude that we have heavy tails. That's Cauchy. And if we see below the line on the left, below the line on the right, this is skew left data, and we can achieve this with the beta distribution if the first shape parameter is exactly 1 and the second shape parameter is greater than 1. All right, so here, like this first one with the difference between iron and silicone, we see below the line on both sides. All right, so it's below the line, we have a skew left distribution. So the difference between iron and silicone is skew left. This is skew left, skew left. Now here we see above the line on both of these. And so there we conclude that it's skew right because it's above the line on both. Let's see if I can get. We see above the line on both, it's skew right, skew right, skew right. Now this is pretty close to normal, pretty close, and it's okay to have a little bit of deviation left and right. It's when it severely goes away, when it severely moves away from it. Then I need to, make a judgment call. Now, if I see deviation from the middle, like third of the plot, it's severely not normal, and basically all bets are off. This technique doesn't work. It has to be relatively well-behaved data, unimodal, continuous data. All right, so so we can see the results line by line. So here, this feels like it's pretty close to normal, for the aluminum row, kind of interesting. And you'll notice that in the previous plots, that when I didn't have something different for the numerator denominator aspect, what happened was this plot was a reflection of the others. So if you scroll back up, you look at the points, you look at the smooth LM, the smooth lowest plots, above and below the diagonals are reflections of each other. Here, this is not the case. Check out that this is pretty close to a straight line. This is definitely not a straight line. Big difference in these. And so with these, we can see that we're actually getting different information that's more complete. I think it's really slick what the authors of this package did. And we also do pairwise plots of the log ratio box plots. And so here, a box plot is a 5-number summary. We have the minimum, we have the maximum, we have the 25th quantile, 75th quantile, and the 50% median. All right. And so it's a 5-number summary. As data scientists, we love these. Don't show them to your stakeholders. Stakeholders hate box plots. Whiskers extending along the diagonal values correspond to approximately 99% of the data for normally distributed data. Now, something about this is every single software package that you use, every single, if I use Python, if I use R, SAS, different packages in R, will actually have different rules for their box and whiskers. So there's different ways to compute quantiles. There's different ways to compute the whiskers and the outlier aspect. So don't get hung up on particular values. It's just that the vast majority of the data is within the whiskers. And so like here, from there to there, for silicone composite residual, I can see that the vast majority of my data is within those two things, those two ticks. Outside the ticks are outliers. Now, what are the outliers criteria is going to change by package and by function. So, and in base R, we can control these aspects. All right. All right, I hope you are as excited about this as I am. We need to use these to get a good, solid understanding of our data before we start doing our modeling, before we do our hypothesis testing. These are some really good tools to be able to produce good, solid data analysis. That's all I've got for you. Life is short. Do math.